Okay, welcome everyone. I'm very pleased today to introduce Professor Yvonne Stokes from the University of Adelaide. Yvonne is an applied mathematician who studies a range of industrially motivated problems in fluid mechanics, particularly involving slow viscous flow. So Yvonne's done lots of work on glass production and optical fibers, and also work on flow in curved ducts in various different applications, which is something she's going to be talking to us about today. Yvonne received her PhD from the University of Adelaide. Following on from that, she has become a faculty member there and is now a professor. Yvonne won the ANZIAM, Australian New Zealand Industrial and Applied Mathematics J.H. Mitchell Medal in 2007 for outstanding early career researchers, and then the 2018 EO Tuck, Only Tuck Medal, which is for outstanding mid-career researchers. It's very fitting as Ernie Tuck was one of Yvonne's PhD supervisors. Okay, I'll leave it there and I'll hand over to Yvonne to talk about inertial particle focusing in curved microfluidic ducts. Thanks, Yvonne.
Thank you, David, for that kind introduction, and thank you for the invitation also to speak here in a somewhat different format to normal, but it's nice nonetheless. So, as David said, I'm going to be talking about flow in curved geometry, in particular a curved microfluidic duct, and it's a flow which has got particles in it. The work is motivated by this device that's pictured on the left side here of the screen. It's called a spiral inertial microfluidic sorter. I'll talk about that a little bit later. And I just want to acknowledge that I've done this work in collaboration with a couple of people. First of all, Brendan Harding. Some of you have probably met Brendan at ANZIAM conferences. He was a postdoc with me on an ARC grant in which we begun this work, and he's now at the Victoria University of Wellington, although remotely because he's stuck in Melbourne, or in Ballarat actually, but in Victoria. And the other person that's involved is Andrea Bertozzi at the University of California in Los Angeles. And finally, I need to acknowledge the ARC that had supported this work and my own University of Adelaide. So as I said, this work is motivated by this spiral inertial microfluidic sorter, and this is a device. Just going to get this to work. Can't seem to. Right. Okay, this is a device which is actually used for something called liquid biopsy. So what is liquid biopsy? Let's move this so I can see my own screen. It's the isolation of circulating tumour cells, which are here going to be shortcut going to be CTCs, from a routine blood sample. I don't know what's happening here because I can't seem to go on. Let's try. Okay, so this is just a quote from a paper by Ferreira, Romani and Jeffrey from Molecular Oncology about liquid biopsy. So it says here, circulating tumour cells are a component of the liquid biopsy and they hold great potential to transform the current landscape of cancer therapy. And a key challenge is to unlocking the clinical utilities of circulating tumour cells lies in the ability to detect and isolate these rare cells using methods amenable to downstream characterisation and other applications. I probably should just say liquid biopsy really just means taking a blood sample from a patient and then putting it into a device and trying to find these tumour cells circulating in the blood. So that's essentially what it is. So if you can find them, examination of these cells has potential to determine patient prognosis. Obviously, if there's cells in your bloodstream, you're in danger of the cancer spreading elsewhere. So that's sort of a prognostic reason to be able to identify them. It helps you monitor tumour recurrence and also therapeutic responses to drugs and so on, and also identify new therapeutic targets. And there's no doubt about a batch of other things. There's a couple of more things there that I've got as well. And 90% of cancer-related deaths are due to metastatic cancer arising from CTCs. The nice thing about liquid biopsy, if you just take a blood sample, it's a relatively non-invasive method for trying to find these cells compared to some methods used today, like, for example, sentinel node biopsy, where you actually try and take out lymph nodes and find cells there which indicate that they're into the vascular system. So it's a preferable thing to that. And obviously, if we can identify these cells, we have the ability to do something about treating the patient, and hence in improving or increasing the potential to improve the lifespan of the individuals. So just to say a little bit more about how this sort of works. So you take a blood sample, and it's a mixture of cells, of course, and blood plasma. Normally the blood sample is modified, so it's diluted, and also they remove the red blood cells. So you get left with white blood cells and the circulating tumour cells if they're present. And the idea is for this sample to be pushed along using a pressure gradient, this spiral channel, which has a particular cross-sectional structure and some curvature because it's curved. And as it flows, the cells sort or move, migrate across the cross-section and focus to different places in the cross-section according to their size. And the idea is that by the time it's gone down the spiral at the far end, as shown in the centre here, you can split the channel into two and hopefully collect the circulating tumour cells in one pot and the white blood cells in the other, and hence you can find these cells. So there's a little cross-section showed at the bottom here of the cross-section of this channel here. It's trapezoidal in cross-section, and you see the larger cells are on the sort of inside of the bend. These are your circulating tumour cells, and the white blood cells, which are a bit smaller, should collect on the outside of the bend. And I'm not sure how clear it is, but there's some sort of streamlines of a cross flow in this channel. The primary flow is down the duct, but because of the curvature, you get a cross flow. So this is actually one of the most promising methods for liquid biopsy, and a commercial version's already been developed by a company called Biolitics, which are based in Singapore, and it's called the ClearCell FX1 system. It's a very simple device, it's robust, you can get a high throughput with something like this, and it has minimal impact on cells. So that's things that are nice about this device. But there are some difficulties, and that is in getting the desired isolation of the rare cells and not having it contaminated with white blood cells or leukocytes. So being able to do that properly is a key to this device working. So a lot of experimental work's been done, but there's not much quantitative understanding, and it's needed to understand how geometry, particle size and weight and flow rates all affect particle focusing. And if we can understand that, then we can hopefully improve sorter design and selection of operator parameters for a specific task, because different cancers have different cell sizes and weights. And so you have to build your sorter to get the cells you're looking for. So this is the problem that's motivated our development of a model to give insight into how the interplay between the various forces on the cells affects their focusing position. So the forces that come into play here are something called inertial lift, which I'll talk about just shortly, and then drag due to the flow, and also we have gravity. Okay. So first of all, to inertial lift. So this is something that was reported by Segre and Silverberg in Nature in 1961, so it's been known for quite a long time. What they did, they did an experiment where they took a mixture of fluid and particles. It was uniformly mixed, and they made it flow along a pipe. So this picture on the left here is a cross-section of the pipe. The fluid's coming in from the top, and as it goes along the pipe, the particles within that fluid actually migrate. You can, this is just a straight pipe, so there's only streamlines from top to bottom vertically, but the particles actually migrate across streamlines, and they collect finally in an annular region, which is sort of shown down here at the bottom. And this, for their experiment, it was about 0.6 of the pipe radius. That was the radius of this annulus. So they identified what they called inertial lift as the mechanism for this, and inertial lift is essentially due to the inertia of the flow when it comes into contact with particles, and you get, because of the change in the flow rate on the different sides of the particle, if you will, you get forcing on the particle, which makes it migrate across streamlines, and that's been called inertial lift. So this work sparked a lot of experimental and theoretical study, not surprisingly. In 2004 and 2009, there were papers by Mattis and some co-workers, and they showed that the radius of this annular region actually increased as the Reynolds number of the flow increased. De Carlo, Borchiani, and others have also looked at this mechanism of inertial lift as for separating cells by size in microfluidic ducts, which is, of course, the problem that motivates this talk. So much of the behaviour, and this is especially in complex geometries like curved microfluidic ducts, is only understood at an empirical level. So there's been a lot of experimental work, but rather less modelling and theoretical work. Okay, so let's start by looking at straight ducts before getting on to curved ducts. So studies done by De Carlo and others, there's a just one paper given there, have shown that if you have neutrally buoyant particles, they typically migrate towards one of 4 equilibrium positions, which are located a finite distance from the centre of each wall. I've got a little picture at the bottom here to just illustrate what's going on. So on the left is a square duct. So this is just showing a cross-section of the duct. And on the right is a long rectangular duct. These are pictures produced by Brendan Harding, not in this other work, but they illustrate what goes on. So what you see is there's the 4 green points here. They're actually like, I guess you might think of them as sinks, if you're familiar with sort of terminology in fluid mechanics. They're points towards which the particles flow. And there's 4 of them, one adjacent to each wall and in the centre. Okay, so this is a perfectly symmetrical problem because we've got a nice symmetrical channel and we've got no curvature. The red dot is like a node or a source. Particles will move away from that point. And the yellow dots are like saddle points. You can sort of see the particles that are moved towards and then away from them and go to the green points. So when you have a straight channel, you get these 4 green nodes to which the particles migrate at the centres of each of the walls and just off from the edge. The dashed line here actually indicates the closest that a particle can get to the to the wall. The centre of the particle would lie on this dashed line if one edge was touching the wall. So this was shown in various studies, including that of DiCarlo there. Some theoretical work was done by Hoodley and Roper. So Caitlin Hood was a PhD student at UCLA, and she did her thesis on this type of inertial migration of particles, and she developed a model of inertial lift force at small particle Reynolds number for neutrally buoyant particles in flow through square ducts. So she first of all focused on the square duct and did a little bit of comparison with experiments and showed the model to agree reasonably well with the experimental data. She then looked at rectangular ducts as well, and saw that the region of capture on the side walls, so that's shown down again down the bottom here, actually decreases for the points on the two side walls. The region of capture for these 2 points becomes much smaller than the top and bottom one. So most of the particles will just go to these 2 positions with relatively fewer particles to the side walls. Depending on the width and height, you can even have these 2 sinks on the side walls disappear. So that's the width and height, and also the particle size. Other studies have indicated you get less focusing at high flow rate. So if you increase the flow rate through the channel, you can actually have less focusing. And this suggests that lower flow rates are more useful for cell separation and sorting. So of course, the work I've been doing has been looking at curved ducts. So focusing behaviour in curved ducts has been mostly confined to experimental studies. So there's a couple listed there. And the experiments have shown that curved ducts are effective in the separation of particles or cells by size. And I guess that's also indicated by a company having developed this microfluidic sorter. So it's been found that the height to width ratio of the duct being small, so much less than 1, is actually favourable to focusing particles by size. And what happens, as I already mentioned earlier, is we get a flow along the channel. So on the left-hand side here, I've just got contours of the primary flow down the channel. So it's along sort of curved lines or paths. And then in the cross section, which is shown on the right, you get the what we call the secondary flow. So it's just like a pair of counter-rotating vortices, and the flow sort of going out roughly in the centre and then going up or down, as the case may be, on the edge and flowing around the top. So this is what's called Dean flow. It was identified by Dean in 1927. Paper appeared by Dean and Hurst in 1959 about Dean flow in pipes, just with fluid, no particles. So it's called Dean flow. And that's the type of flow that exists in these curved ducts. So the interplay between the inertial lift force, once you put particles into these flows, you get a inertial lift due to the fluid against the particle. And you get an interplay between that lift force, which is primarily due to the axial flow. But then you also get some drag as the particle migrates in the cross section, which is coming from this secondary flow. And the interaction of these two is very important in particle separation. So we've been building up a model of this, and here are some model assumptions. So we start by assuming we have a very long duct and we have no end effects. So we're not worrying about the entry and exit to the duct. We assume a dilute limit so that there are very few particles, and so consider a spherical, just a single spherical particle here. We also consider a constant bend radius. That's all I'm going to be talking about today at any rate. Obviously, when you have a spiral sorter, the bend radius is changing, but it's changing slowly, so it's not too bad to just look locally and consider a constant bend radius. We have a pressure-driven viscous flow. The axial flow along, which is just along the duct, that's what I'm calling axial flow. It's in a curved path, but it's just along the length of the duct. And that's large compared to the secondary flow velocity, which is a lot smaller. Far from the particle, the flow is that of a particle-free fluid, and we call that the base flow. And then near the particle, the base flow is perturbed by the particle. This is how we think of it in building the model. And this is actually following the work of Caitlin Hood. So we get a slow migration of the particle in the cross-section compared to its axial velocity. It's sort of moving down the channel or the duct quite quickly, and it's migrating across the cross-section slowly. And because of that, we can consider the particle to nearly follow a streamline of the base axial flow. So just think about the base flow and just the component of that flow along the channel. And so you sort of get straight, they're not straight, but just curved paths that follow the curvature of the channel. And you can think of a particle just traveling along such a path. And then the particle is perturbed from that path in the plane of the cross-section by the drag force from the secondary flow and inertia due to the curvature of the path itself, and then inertial lift as well, and gravity. Okay, so here's the sort of reference frames we use. We use both lab and rotating reference frames. I'm just going to describe these here. So what we're showing here is we've got a curved duct. It's just a constant curvature, constant bend radius. The bend radius is big R, and it's measured from the z-axis, which is vertically up, out towards the centre of this duct. We define a radial coordinate, which is from the centre of the duct out, and the z coordinate is going up. Gravity, of course, is acting down. We've got the height of the duct being big H and the width of the duct being big W, and then we're thinking about a particle in this cross section, which has got some Cartesian coordinate x, but we're going to work in polar coordinates theta, which is an angular position from your x-axis here, a radial coordinate r, rp, I've got the p's to denote the particle position, and then a vertical coordinate z, zp. Okay, so this is just a rectangular channel. We will later look at non-rectangular, specifically trapezoidal channels. So h will be the height of the duct at r equals 0, so here in the centre. And little a is the particle radius. So first of all, a lab reference frame. So the particle centre and the is called xp, and it's in polar coordinates, got a theta, r and z coordinate, as I've already mentioned. It also can spin, so that's given, designated by big omega p. It's a function of time, and its position in the lab, it's moving down the channel, so this position is a function of time. So we've got the particle travelling along, we're thinking of it travelling along a streamline of the base axial flow component. And because of that, we think it's got a constant angular velocity. So d theta p dt is a constant, which I've called big theta here. And that means its position, its angular position theta is just big theta times t, if theta p 0 is the position at time t equals 0. And then because we're at this point thinking about sticking on this curved path, its radial and z coordinates are not changing hardly at all with time. It's very slow. So we think about these derivatives as being 0 and also its spin being constant, so its derivative being 0. But in this reference frame, our flow is unsteady because the particle is moving down the channel. So we now move into a rotating frame, and instead of sitting in the lab and watching the particle go along the duct, let's move along with the particle in the cross section of the particle. And then what happens as you're moving along, it really seems like the walls of this duct are moving back the other way. So your duct is sort of rotating about the particle, and it rotates about the z-axis with an angular velocity which is big theta. So we've still got the particle centre and spin, but we've got primes on the variables. And because we're sticking in the cross section of the centre of the particle, its angular coordinate, theta prime, subscript p, is 0. Okay, so that's because of our rotating coordinate system. So theta prime p is always 0, and its radial coordinate and z coordinate is the same in both the lab frame and the rotating frame, and we're thinking of them as changing very slowly, so essentially the derivatives are 0. And then our spin of the particle is still a constant. We're thinking of it as being constant anyway. We've had to subtract off the angular velocity of our moving reference frame from it, but it's still a constant. So in this reference frame, because we're travelling with the particle, we're just seeing sort of the flow, the base flow perturbed by the particle, and the flow is approximately steady. So we can look at a steady flow model instead of an unsteady flow model. So we start by writing down the mathematical model in the lab frame. So we've got a base flow, which has just got a bar over it here, the velocity and the pressure, functions of RZ and theta, or P is a function of theta, but U is just a function of R and Z in the base flow case. And it's just a steady pressure-driven incompressible Navier-Stokes flow problem with no slip on the duct boundaries. So for people that are sort of familiar with fluid flow equations, it's sitting here, and it's a fairly standard type of fluid flow equation. This is how we write the pressure that drives the whole flow, and we've got no slip, so U equals 0 on the duct boundaries. Now we put a particle into this flow, and so the presence of the particle changes the flow. So instead of putting bars on, we've taken the bars off to denote the flow and the pressure when the particle is present. And now all of these, both the velocity and the pressure in this lab frame, are dependent on time as well as position. So it's an unsteady pressure-driven incompressible Navier-Stokes flow problem, still no slip on the duct, and it's also no slip on the particle surface as well. So the problem looks pretty similar to the base flow, excepting we've got this extra equation which says that the flow has to move with the particle itself. Okay, so with both its translation as well as its rotation or its spin. We can also write down the force and torque which drive the motion of the particle. There's a component due to gravity here in the forcing, and then the part due to the flow. And the main reason I'm writing this down is just putting it here on the slide, is to illustrate that we actually determine the force and also the torque by integrating the flow that we solve for over the surface of the particle. Okay, so that's what the model looks like in the lab frame. We then move into the rotating frame, and to do that we've got to sort of take off the rotation from the flow. So the base flow and the flow in the problem with the particle just have to be modified as shown here. The pressure really doesn't change too much, except it becomes independent of time because we consider this a steady flow problem. So it's just a matter of doing a translation from one set of coordinates to the other. And then we assume the flow is steady. So we drop all the time derivatives from the momentum equation. And then the next thing we do is we rewrite the problem in terms of the disturbance velocity. So it's the difference between the flow and pressure in the problem with the particle, which is disturbing the flow, and the base flow. So we just write it down. The flow is this V prime, and Q prime is the disturbance of the pressure. We scale our variables, and I haven't bothered to put up the scalings here, but by taking appropriate scalings, we get our momentum equation written out in terms of a Reynolds number, and the Reynolds number that's important in this equation is the particle Reynolds number, which I've written here. So this first part, rho um h on mu, is the flow Reynolds number, if you like. Um is just the velocity at our origin of our RZ coordinate system. And then the particle Reynolds number is the flow Reynolds number multiplied by the ratio of the particle radius to the height of the channel squared. And this is a number that we assume to be small. So it typically is quite small, much less than 1, but it can get to be order 1, but we're going to be assuming here that it's much less than 1, and that means we can derive an asymptotic model using standard methods, which I'm not going to go into, but we do get an asymptotic model in terms of this particle Reynolds number, and we drop higher order terms and get a simplified model. We sort of get a leading order model. So the force and torque on the particles can be written in the way I've got here, sort of fairly standard sort of expansion in terms of the particle Reynolds number. You get a term which is order 1 over the particle Reynolds number, so it's quite big, and then the next order term, and then higher order terms, order of the particle Reynolds number, and smaller, we drop. There's an expression for the force and an expression for the torque to stay two terms. In the problem, we've got to choose this angular velocity at which the particle is moving downstream, and also its spin, and they're chosen such that the components of the force and the torque, the leading order components of the force and the torque, which are due to just the axial velocity component, are 0. So we're sort of assuming that the particle's moving along steadily in the axial direction, and there's no force or torque that's acting axially. And we're just worrying then about the force and the torque, which are causing it to move in the cross section. Once we've done this, we can, take a particular particle size and maybe some relative density if we don't want to take a, even if it's a neutrally buoyant particle, it would have the same density as the flow, but it could be lighter or heavier as well. We take a particular duct size and shape, and then you can compute the force on a particle depending on its position within the cross section. So you just have to think of F prime P here as being a function of the particle position within the cross section that you've chosen to look at, and for the particle size and density that you've chosen as well. You can then compute the trajectory of a particle within the cross section, and to do this we base it on what we call the terminal velocity, as actually done by Caitlin Hood as well in that work in her thesis, where you think of the particle velocity in the cross section at which the drag force is equal and opposite to the perturbing force F prime P that you compute when you're thinking of the particle as being fixed and not able to move. So you sort of think of your particle being stuck on this curved path so that it can't migrate in the channel, compute the force, and then say, okay, now it moves. And that will create drag, and you have you think of its velocity as being that at which the drag and this perturbing force are equal and opposite. So that's all I'm going to really say about the model. It's quite complicated, and there's some papers if anyone wants to look it up, and I'll just was going to try and present some results now. So first of all, I'm going to be thinking about neutrally buoyant particles, so particles which have the same density as the fluid in which they are. All the results are set with the length scale of half of the height of the channel at the origin, so that's h on 2, and the carets are just the particle radius, the duct bend radius, the height and the width of the duct, all scaled with h on 2. So because I've scaled h with h on 2, it always has a height of 2 at r equals 0. So here's some pictures of force fields, and at the top we've got force fields for some different particle sizes from 0.05 up to 0.2 for a bend radius, a scaled bend radius of 160. At the bottom we've got the force fields for the same set of particle sizes, but for a bend radius which is infinite. So that means it's a straight channel. So you can see how the force field is changing. The colour sort of indicates magnitude of force. What's more useful to focus on here are the contours. So there's some black contours sitting in here and some white ones. And the black ones are contours of 0 horizontal force. The horizontal force component will be 0 if you're sitting on this black curve. Okay, and the vertical component of the force, this perturbing force, will be 0 if you're sitting on the white curve. Okay, and the arrows indicate the direction of the force as you move either side of the curve. So if I move above this central horizontal white line, the force will be down. And if I move below it, the force will be up, and so on. So with the black one, if I move from my cursor to the right, the force will be back towards the left. And if I move, towards the left of that curve, the force will be towards the right. Okay, so you can sort of pick up from these force vectors, the vector field, if you wanted to draw the full vector field, the way the particle will move. But the other thing you can see on these pictures is where the white and the black curves intersect, there's no force on the particle at all. So at an intersection point of these two black and white curves is a steady state, because the particle will be undergoing no force, and therefore it will just stay there. So as this set of pictures is for a constant radius of a bend radius of 160, and the particle size is increasing as you go from left to right, and you can see the force field is changing, and these black and white curves are changing, and also the position of their intersections are changing. And by looking at the forces, you can work out whether one of these intersections, so these steady state points, is stable or unstable, whether a particle, if it moved slightly off it, would go back there or would move away. So it's probably easier now to move to pictures of particle trajectories. So these are trajectories of particles. So it's the same set of particle sizes, same bend radius of 160. And now the dots are showing the steady states, and the colour of those dots is indicating whether they're stable or unstable. So if you see a red dot, it's an unstable node, right? If the particle was here, it would be at a steady state, but if it just moved slightly off it, it would never go back to that red dot. It would move somewhere else. The yellow ones are like saddle nodes, and green indicates a steady state. So in this picture on the left, we don't have any green dots. What we have is a green orbit. So in this case, the particle will just rotate, will migrate to this green curve, and will just rotate. So in the background, which is not shown in the picture here, is of course the secondary flow. And essentially the particle is so small that it migrates to a point, but then it just gets carried on this orbit within the secondary flow. By increasing the particle size, you actually increase the lift force, because you get a bigger change in the flow velocity from one side of the particle to the other, and so more forcing. So the particle still goes to an orbit around a source, but it gets there much faster. You can see the trajectories over here, they're long and winding, but over here it goes quite quickly to this sort of what we call a slow manifold, and then moves down here and then hits onto the orbit here. Okay, so increasing the particle size more, so I've gone 0.05, 0.1, now 0.15, and now suddenly we lose the orbits and we get a point, a steady state, which is stable. So the particles will migrate to this point and focus there. So we've just seen how that for the particular geometry here in a square duct, particles of different size will behave differently. And increasing the particle size again hasn't really changed the basic behaviour. We've got a big change in the basic behaviour from a particle size of 0.1 to 0.15. Now the set at the bottom here is just for a straight duct, and you can see that basically you have the same behaviour as the particle size increases. You have the 4 stable nodes, and the 1 unstable node, and the 4 saddle nodes. And that's the case no matter what particle size you have here. Okay, the position of it changes a little bit, but the behaviour doesn't change, and you always have there's nice symmetry here because it's a straight channel, and you always have the particles collecting in 4 different points, compared to above with the bend. And now we've got the particles focused to 1 point. So this set of pictures is to show how bend radius can affect the particle focusing position. So before I was showing how size changed the position. So on the left, I've got particle size 0.1 and 2 different bend radii, 210 and 220. And you can see that by changing the radius of the bend from 210 to 220, we've gone from a nice orbit here around an unstable node to having a stable node very, very close to the unstable node, and this is where all the particles will focus. On the right's a similar type of thing. It's a bigger particle, 0.15, smaller radius of 80. Again, we have orbits and then going to a single stable node. So that's what we get there in a straight channel by changing the radius of the bend. So now we go to a rectangular channel instead of a square channel, and similar sort of behaviour in a way, but it's a bit more stretched out. So on the bottom is the straight duct, so infinite bend radius, and we still get these 4 nodes. You notice that as the particle size goes from 0.05 to 0.1, the 2 stable focusing points on the side walls have vanished, and we've got 2 saddle nodes here instead. So we've just got the particles focusing to these, the top wall and the bottom wall at the centre of the wall here. But by having a bend radius here of 160, the top set, okay, on the left we've the particle travels with the background flow, but it does eventually reach a focusing point here in the centre of this spiralling path. But increasing the radius, you go there much more directly. Okay, so we've got these 2 focusing stable focusing points and 1 saddle. Okay, and their position is changing horizontally as well as the particle size changes. So you could imagine that if you have 2 different particle sizes, say 0.1 and 0.2, that you get slight separation between them, just based on size. So if you increase your width to height ratio even more, so make a much longer, thinner channel, you get a bigger change in the focusing positions, but very similar behaviour still. Okay, as the particle size changes, its focusing position is changing as well. And then you've just got the straight duct case on the right to compare with, where there's no change in where the particles focus. There's no way you're going to get separation of particles of different size in a straight duct, but in a curved duct, you might, if you're clever enough to divide your flow at the right place. So we can plot the focusing position as a function of the bend radius. We're thinking of the bend radius as being epsilon to the -1, so it's a fairly large value because the radius of the bend is very large compared to the height of the duct. So if we plot the focusing location, and here we're just talking about horizontally, I'm not worrying about the vertical position because finally the flow is split horizontally. So this is just sort of the R coordinate, if you like. And as the bend radius increases, its focusing point changes, and the change, the way it changes depends on the particle size. So the blue is for the smallest particle, or the dark blue is for the smallest particle, and the light blue is for the largest particle. And then we've got 2 different sets of curves here, one for a width to height ratio channel of 2, and the other one is twice that, width to height of 4. Okay, so they look pretty messy, but interestingly, if we now plotted the same thing, but against this parameter we've called kappa, and kappa is a measure of the secondary flow, the ratio of the secondary flow drag to the inertial lift force. And it's given by this dimensionless group here. And when you plot it like this, all of these curves collapse, at least for a small enough kappa. So order 10 and smaller, our curves have essentially collapsed. You get these 2 bits at the bottom because these arise where you get more than one focusing point, but these focusing points have a fairly small capture region, so they're not so important. But it's pretty nice that you get this collapse of all these curves onto one another. This is for a width to height ratio of 2, and then on the right, a width to height ratio of 4. So this could be a useful parameter to predict particle focusing for based on the height of the duct and the bend radius and the radius of the particle. So now let's look at some non-rectangular channel cross sections. So trapezoidal have been used a lot experimentally, and hence we've looked at these, and it's been found experimentally that trapezoidal cross sections lead to better particle focusing than a straight rectangle, and that's borne out by the model here. So we have on the right 3 pictures for 3 different particle radii, all with a bend radius, I've written here as epsilon to the -1, of 160, still just the scaled bend radius. So for the smallest particle, it goes through a lot of spiraling in its trajectory and hits these 2 nodes. And now, because we don't have top to bottom symmetry, you'll see there's a little bit of an offset in the position of the top and bottom focusing points. And then just by increasing the particle size from 0.05 to 0.1, instead of being, you know, closer to the high end of the trapezoid, we've gone to the low end. By the way, the bend axis, the z-axis, is out on the left here. So now we can start to see how you get potential separation by size. If we increase the radius again, the particles move back to here. So you can see with no bend radius, or an infinite bend radius, sorry, no curvature, so a straight duct, basically the focusing position isn't changing. So the bend is incredibly important to getting different focusing positions for different particle sizes. So once again, we can plot the scale bend radius, or epsilon to the -1, on the left hand, and the focusing location horizontally on the vertical axis here for different trapezoidal cross sections. So on the this is for one with a WH on 4 = 4, so that's the width of the trapezoid divided by the height at the centre is 4. And then when you plot it in terms of this kappa parameter, again we get a collapse for kappa, you know, up to about order 10, which is nice. So similar behaviour to the rectangular channel case. Just so you can appreciate that what you get is very dependent on lots of things. So here we've just dropped the bend radius down to 80, and suddenly things have changed a lot. So we've got 4 stable focusing points instead of 2 as before. So geometry is very important to what's going to come out of here. Just thought I'd illustrate that. So am I out of time?
Yeah, if you could wrap up.
Yeah.
It would be, we started a couple of minutes late, sorry.
Okay, so I was going to talk about non-neutrally buoyant particles as well. So now gravity becomes important. So maybe you just, this is a moderate to large Froude number. So we've got, you can see, well, I don't know what size your screens are, but anyway, we're going Froude number squared from 10 up to infinity. So that's sort of gravity becoming negligible at a very large Froude number, and more important at the smaller size. And then looking at a difference in density. So we have this sort of relative particle density. It's the ratio of the particle density to the fluid density subtract 1. So rho s would be 0 if the particle had the same density as the fluid. And so you can work out the horizontal position versus this relative particle density for different Froude numbers, and the horizontal and vertical lines, the intersection point here is if rho s is 0. So you can sort of see how the focusing position changes. This is in radially. The crosses are for the lower side of the rectangular duct, the lower, and the pluses, sorry, the crosses are for the upper and the pluses are for the lower equilibria. So, and then up the top here, we've plotted the Z coordinate. The Z coordinate really barely changes, just shown here, with density. But the radial position changes quite a bit with density. And just one thing to point out here, we've got a picture up here of a 0 rho s. So this is a particle with the same density as a fluid, and an infinite Froude number, which means gravity is not important. And this is the case for a neutrally buoyant particle. But we can have a heavy particle, so ρs is 8 now, and still a very large Froude number, and it makes a small difference. It's not so visible here, but it does make a small difference to the position of the focusing points, not because of gravity, because gravity is essentially not affecting it, but the actual centrifugal force due to the inertia of the particle still makes it change radially, its position radially. So it's why you get not much change in the vertical position of the particle, but you can get substantial change, or relatively more change, in the radial position of the particle. Okay, so if we look here at a bigger particle size, you can see, you know, somewhat more change in the particle focusing positions. So I won't dwell on it. This is for a relatively large Froude number squared being 10 or higher. If we make the Froude number to be order 1, so gravity is quite important. You can see this is a buoyant case, ρs is negative, and the particle's going up rather than settling down. This is the neutrally buoyant case, and then the heavier side where the particle will sink. Okay, you can sort of see that even though the particle density is changed here, it's all the same particle size, the focusing position hasn't barely changed at all. So changing the weight doesn't look to change the particle position very much. Changing the particle size changes it a little bit. Okay, so just to wrap up, a few comments. The model is not restricted to rectangular and trapezoidal cross sections. We've focused on them because that's what's used in experiments, but we could actually do any geometry we chose. Clearly the cross-section shape, the bend radius, the particle size and gravity affect the focusing position of particles. This kappa we found is a good parameter which gives the ratio of secondary flow drag to inertial lift force. And if we have a kappa less than around 10, it approximately determines the horizontal focusing location for nearly neutrally buoyant particles for some given channel cross-sectional geometry. I haven't shown it, but it's not nearly, doesn't appear to be so useful once you have gravity in the problem, or non-neutrally buoyant and non-neutrally buoyant particles. So inertial focusing looks most effective for separation of nearly neutrally buoyant particles by size. It doesn't look so clearly effective if we were trying to separate particles of all of the same size, but separate them by weight. That wouldn't, doesn't look to work as well. So there's lots of future work. Experimental validation would be good. We haven't really done that at the moment, apart from looking in papers and trying to see if our work corresponds, and it corresponds on a qualitative to a qualitative level, but we need to look at things more quantitatively. And the one thing that really needs to be done is to look at particle position over time, rather than just looking at sort of the steady state positions after long enough time to reach them. We need to actually explore how things evolve over time, and also explore other cross-sectional geometries. So I'll leave it there and say thank you. And if anyone's interested, there's a couple of papers. One's out, and the one on gravity has been accepted by JFM and should appear shortly. Thank you.
Thanks very much, Yvonne. That was really nice. There's a lot of nice pictures there. Very informative. Okay, we have maybe filled up our time. So if anyone needs to leave, feel free, but I'm sure we could ask a question or two to Yvonne if anyone would like to. Anyone should be able to unmute themselves and shout out if they have a question. Well, just to, in case someone's waiting for a question, I'll ask something. So I wonder, in these, the actual microfluidic sorters, do you have an idea of the relative size of the particles to the channels, and also sort of the concentration or volume fraction of the particles that's sort of typical?
Okay, so we do. I can't tell you off the top of my head. I'd have to look it up. The volume fraction is a little bit more challenging. So there's a paper actually, which I think it might be a Walkiani paper, which goes through a whole procedure for how they prepare the sample for putting along one of these sorters. And so it gives you, you know, a number of cells per volume, but then they dilute it down quite a lot.
Okay.
And modify it. So it's far from real blood. But yeah, it's certainly got a lot more cells to one. This is much more simple, but you know, it's just where we've started. It seems to be fairly well recognised. So we've talked to DiCarlo, he's at UCLA quite a bit, and he's going to do some experimental work for us. And he says that even in suspension, you know, multi-particle suspensions, they do tend to behave very similarly to what an isolated particle does, at least in long enough time. So we're sort of hoping that our single particle model is going to give a good prediction.
Sounds reasonable. Yeah, that'd be very interesting to see.
Yeah.
They have all that imaging stuff. Okay. Anyone else like to jump in and ask a question? All right, well, we might leave it there. Let me stop.